This is a video on titrations. It's to serve as a mini lecture. However, most importantly, in your titrations packet, there is a video link. I've been having a hard time with the first link, but if you go to the EduTube link, that is the link you want to look at while you're working on this packet. However, there are a few things I want to point out to you in the packet that I think are very important. The first are these two graphs down at the bottom. So a titration is simply adding either an acid to a base or a base to an acid, or honestly anything that reacts with something else. So you can do titrations with redox. So if I look at this one, it starts down here, which is telling me it has a low pH, because I look, this left side is always going to be pH. So down here I have a low pH. So originally in my beaker I must have an acid, because as I go up I have a high pH, which means it must be a base up here. So this kind of titration curve is a very common one. It means that in my beaker or my Erlenmeyer flask I have an acid and I'm titrating it with a base. So for example, if you look at the little diagram, the base would be in this contraption that would allow it to drop down into my Erlenmeyer flask. This is called a burette, and this is called an Erlenmeyer flask. So the acid would be in here, and this is where my pH probe is to find the acid, and then the base would be in my burette. This graph, however, is slightly less common, but you could definitely see it. And what you have here is a very high pH, which means you start with a base. So what that means is in my little Erlenmeyer flask, I have a base and I'm adding an acid to it. So that down here I've added so much acid, the pH is very low. Now, what you notice is both of these have an equivalence point where it seems like they're at 7, pH of 7, which would tell me that it's neutral. Well, if I add a strong acid to a strong base, or a strong base to a strong acid, I will get an equivalence point at a pH of 7. What that means is my moles of acid equals my moles of base. So at this point, at a pH of 7, I had to add 25 milliliters of OH minus to get a pH of 7. Now, given that, if I know moles of acid equals moles of base, and I'm sorry you can't see this, I'll move it up. Well, I know to find moles of acid, I take the molarity of my acid, multiply it by the volume of my acid, equals the molarity of my base times the volume of my base. Well, here's the thing. We know the volume of our base, and we probably know how much acid we put in this Erlenmeyer flask. So my volumes are all set. You probably know the molarity of the base. Normally the thing that's in the burette you know the molarity of, and you're trying to figure out the molarity of the acid in this beaker. In this situation, it would just be the opposite, but same equation, molarity of your acid times volume of your acid equals molarity of your base times volume of the base. Now if you flip the page, what you'll start to see is a few interesting curves. So if I look here, this has an equivalence point at 7. So this has got to be something that's strong. However, I start seeing equivalent points that aren't so much at 7 now. And I'm going to see that when I have either a weak base or a weak acid. There are a few important other things aside from just watching the video. One of the most helpful things, and this is on the last page, if you look at the half equivalence point, so if it takes, say, 10.5 milliliters to get to the equivalence point, then I'm going to look at 5.25. And at half that, the pH equals the pKa. And that's actually just a really cool trick to know when you're solving some of these problems to help you out. And if you look at the graph below, the buffering region is in this straight region because you don't see a slope of the line. So all of a sudden, when I start dramatically changing my pH, that means my buffer no longer works. So somewhere around here, I reached buffer capacity, and I can't buffer it anymore.